Okay, now we'll see how to draw the layout of your common source amplifier. To draw the layout of your common source amplifier, go to launch, layout Excel. So the startup option will come, press OK, and this open file option will come. Again, press OK and press yes. So you will get this layout option. So to get your NMOS and PMOS, go to connectivity, generate all from source and press yes. Go to input output pins, select all input output pins and press OK. So after that you will get this NMOS and PMOS. So after getting NMOS and PMOS, take all the pins and keep it at one location. So because of the pins, you should not search for pins. Where are the pins? So because of this reason, you keep all the pins at one location. So after that, select this bounding box and delete it. Rotate your PMOS. Right click, you have rotate option. So rotate left. So you take your PMOS, place somewhere here, and rotate your NMOS. Right click, rotate left option will come, and paste your NMOS here. Okay. After placing PMOS and NMOS, to see its layer, press Shift F. So you can see in between polysilicon in green color, source and drain in blue color. That is the connection for metals. So obviously for PMOS, you have P diffusions, but for connection purpose, you have metal here in blue color. Okay. So now after this same for NMOS. So center one is green color, that is your gate, it is polysilicon. Either side you have source and drain. One side you have drain, one side you have source. So for connection purpose, you have metal that is shown in blue color. This one. Okay. So now from the schematic, you should short drain and drain. You should short drain and drain. To short your drain and drain, take a wire. So the shortcut for wire is P here. Here shortcut for wire is P, or you can go to create wiring and you can take wire. After taking a wire, go to the start connection. So start from the drain of your NMOS, go to drain of your PMOS and connect it. If you do double click, the connection will happen. So the width of metal is very huge. Change the width. To change the width of metal which you are connected, select the metal, right click, properties. So give width. So don't give less than 0.3 micrometers. So you can give anything more than 0.3 micrometers. So because this is based on your lambda based rules. Okay. So next, after sorting your drain and drain, next you have to make the connections for your PMOS gate. So you can see here PMOS gate is connected to V bias. So here PMOS gate is polysilicon, but your pin is metal. That is V bias pin is metal. So metal and polysilicon you cannot directly connect it. So because of that you should use a via. The via is M1 to poly 1. Via is M1 to poly 1. To use a via, go to create via. Via definition you have changed that to M1 to poly 1 and place here. From this via, you take wire P and connect to your PMOS gate. Okay. Similarly, your NMOS also, same thing happens. So for NMOS gate, you have to connect V in, but V in is a metal. So V in pin I have placed here, right? So here one of the pin is V in. So V in pin is a metal. So as V in pin is a metal, you cannot connect metal and polysilicon directly. So because of that, take a wire. To take a wire, go to create wire. Wire definition should be M1 to poly 1. Press hide and place here. And take a wire. Connect to your NMOS. Now, here your PMOS total width is 50 micrometer. Total width is 50 micrometer. So as total width is 50 micrometer, for every 10 micrometer, you have to keep a wire called as M1 to P sub. So sorry, it is M1 to N well. You have to keep a wire called as M1 to N well. So because your PMOS has substrate as N substrate, so we'll keep a wire called as M1 to N well. So for that, go to create wire, select M1 to N well. So this M1 to N well wire you have to place for every 50 micrometers. To know whether it is for every 50 micrometers, use a scale. So to use a scale, you can go to tools and you can get the scale, or shortcut for scale is K. Shortcut for scale is K. Type to the one end of your PMOS, drag it and take the other end of your PMOS. So you will get 50, almost 50 micrometer. So now place this wire for every 10 micrometers. First I placed at 0, next at 10, next at 20, next at 30, next at 40, next at 50. Place it at every 10 micrometers. So after that, the scale is not required. You can delete it off your, or if you're keeping it, you don't have any problem. You can also remove the scale. So now what you will do, this wires what you are placed now, these wires are going to act like a substrate connection. These wires are going to act like a substrate connection. So where you are connected substrate of your PMOS, the substrate of your PMOS, you are connected to source of PMOS, and that is connected to VDD pin. So you have to connect the substrate to source of PMOS. So for that, first what I will do, I will short all the wires. To short all the wires, take wire P and short all the wires. So while shorting all this wires, also you can see this blue boundary, right? So this blue boundary should be within this metal. So you should drag in such a way that your deep blue boundary should be within this metal. So zoom it and drag it. So short all the wires. See, you can see this blue boundary of your wire. So that blue boundary should come on this metal. So now this blue boundary, now it came on the metal. You can see this blue boundary came on this metal, or this metal came inside this blue boundary of your wire. Okay, so that you made. So I have left here, right? This metal should come within this blue boundary of your wire. So now connect this to source of PMOS, because I already told you all this wires which I have placed, it is going to act like a substrate, and substrate of your PMOS is connected to source of PMOS. So all which you have shorted, connect that to source of PMOS. So source of PMOS, to make a connection, take again P. So from this metal, drag it and connect here. So I have made the connection. So anywhere you can place VDD. Anywhere on this we can place VDD. We will place pins later. And similarly, when we come for your NMOS, similarly its width is 20 micrometer. Its total width is 20 micrometer. If you use one wire, that is sufficient, but we'll do one thing, we'll also place the same procedure, placing wire for every 10 micrometer. We'll place a wire for every 10 micrometer. So use a ruler and put a scale for your NMOS width and go to create wire and make wire definition is equal to M1 to P sub, because your NMOS you have substrate as P substrate. In NMOS you have substrate as P substrate. So for every 10 micrometers you place a wire, and you can remove this ruler, and same way you short it. Same way you short all the wires, and you see that this wire blue boundary is on this metal. This wire blue boundary, this one is on this metal, or this metal is within this wire blue boundary. You see that. If it is there, then no problem. And this wires which you have shorted, that is going to act like a substrate. So this substrate is connected to source of NMOS. So I can connect this to source of NMOS. So this is nothing but I can connect this to source of NMOS. Okay. So after this, so only last thing left out is placing the pins. So before placing the pins, here I have to put N-well for your PMOS, because here we are following N-well process. You know what is N-well process? So in N-well process, what we will do? In P substrate, we will create a N-well. In that N-well, we are going to create your PMOS. So for this, what I have to do? I have to create a N-well for your PMOS. So to create a N-well, go to create shape rectangle, create shape rectangle, and here you can search for N-well and select N-well drawing. After that, click at one point, drag it so that it covers the entire PMOS along with those wires, and double click it. Then you will get N-well. So as I already told you, we are following N-well process. So because NMOS is formed in P substrate, and in P substrate we are going to form N-well. In that N-well we are going to form your PMOS. So because of the substrate for your PMOS is N-well. So because I used this wire called as M1 to N-well. This wire was M1 to N-well. Here I used a wire M1 to P substrate, because for NMOS the substrate is P substrate. So after that, the last step is placing the pins. So select one and each and every pin. So to see which pin is this, right click, go to properties. So this is VSS pin. So where you have to place your VSS. So you can place VSS either way. So it is only showing here, right? Where you have to place your pins. It is only showing here. So drag at your pin. So either you can draw horizontal way or vertical way. So drag the pin and place anywhere here. You can place on this metal, or you can place on this metal, or you can place on the source of your NMOS, because all are shorted. So I have placed VSS. So next, take next pin. So next pin is V out. So where you have to place your V out. So it is only showing where you have to place your V out. Fly lines, through fly lines, it is only showing where you have to place your V out. So, and you can also see through text where you have to place your V out. So you can place on this metal, exactly on this metal, right? Because you are placing your V out when you, after shorting your drain and drain of your PMOS and drain of your NMOS. This is your V out. So next is your VDD. So your VDD should be connected to source of your PMOS, or it can be connected to the substrate. So substrate, here we are getting substrate connections through wires. So here is my VDD pin. I can place anywhere here. It is only showing here, right? Through text, you have to place your VDD here. So I will place my VDD here. I placed my VDD here. So this VDD pin I can place anywhere here or inside this substrate, inside the blue boundary of the substrate, or on this metal, or on the source of your PMOS, because all are shorted. Okay. So next pin is your V bias. So V bias is connected to gate of your PMOS. So already gate is polysilicon, so this is metal. So to make this connection, we have already used a via M1 to poly 1. So you place this inside this blue boundary of this via here. Inside this blue boundary, you place this pin. So last pin left out is V in. So drag it. So you will connect this to gate of your NMOS. So as gate of your NMOS is polysilicon, you cannot connect directly. So what you have done, for that reason you have created a via. So inside this via you have a blue boundary, right? So inside this blue boundary you place your PN. So now you have finished all your connections. So now you have to make two types of verification. One is design rule check, whether your design is following all the rules, design rules. Okay. So this there will be some design rules. So whether your design is following all the rules or not, you have to verify. Then you have to verify layout versus schematic. So whether this layout is same as your schematic or not, which you have drawn earlier. So both are same or not, that you have to verify. Okay. So both you have to verify here. So to verify here, the tool what we are using here is Asura. Go to Asura, run DRC. So go to Asura to do DRC. Go to Asura, run DRC. Asura, run DRC. So technology, you change this to GPDK 180. After that, press OK. So it is asking for save. I didn't save it. So okay, you click on OK. And Asura DRC run is in progress. Okay. Now the Asura run has completed. So do you want to view the results? You click on yes. So you should get like this. No DRC errors found. You should get like this. No DRC errors found. So there is no DRC errors. So after this, do your LVS check. To do your LVS check, go to Asura, run LVS. Asura, run LVS, technology, make it as GPDK 180. Next press OK. So already LVS data, it is asking for overwriting, press OK. Next again you press OK. So wait for few seconds, you will get the results of LVS. So you got the results of LVS. It is telling that your schematic and layout match. So your schematic and layout both are matching. So you don't have any errors. You can see that all the errors are zeros. And total DRC violation is also 0. So you should get like this. Okay. So after that, you can extract the parasitics. So you can extract the parasitics. So because virtue of its nature, all the materials have some resistance. So when you have two metals and in between you have some dielectric, so obviously some capacitance has been formed. I think people have studied what are the capacitance formed in your MOSFETs. So because virtue of property of its nature of materials, some parasitic resistances and capacitance has been formed. So because of this reason, we can extract the parasitic capacitance and resistance of this design. To extract this, go to Asura, run QRC, run QRC. So after that, press OK. Yes, the procedure for that is go to Asura, run Quantus QRC. So here in extraction, in reference node, type this exclamatory mark and ground. So extraction type change to RC. So you need both resistance and capacitance and press OK. So previous thing will be overwritten. Yes. Press yes and press OK. So so now you're getting Quantus QRC run completed successfully. So now your tool has been extracted your parasitic capacitance and resistances. So to see this, so go to Virtuoso window, file, open. So in this library should be your library, cell should be Common Source Amplifier, view, change to AV extracted, view, change to AV extracted and press OK. So you can see this. So if when you press Shift F, so you can see the parasitic resistances. So now also you can see parasitic resistances. And parasitic capacitance here. You can see parasitic capacitance. You can see here parasitic capacitor. Yes, and you can also see the parasitic resistances. Okay, this is the procedure what you have to follow to design the layout of your common source amplifier. To draw the layout of your common source amplifier. You can see the parasitic capacitor and parasitic resistance. with its value. You can, if you zoom and see, you will get those capacitance and resistors. Okay. So this is the end of your common source amplifier.